Well, we're almost at the point where we can do an efficiency evaluation of a motor system, but we have to think about both the input energy and the output energy. So the purpose of this video is to get us to recognize how one can consider those particular aspects of a motor. Okay, so here's the first of two important energy ideas. The question can be asked, how much electrical energy must be provided by the battery if you want a motor to spin? And while we won't speak directly about the energy, we can talk about the electric power. You'll see that that is really a related quantity in just a moment. But we can talk about the electric power very, very simply. And that is just the product of the input voltage and the input current. So if we can measure those or somehow calculate those or just know those values somehow, the voltage times the current will be power. The V must be measured in volts and the I has to be measured in amps, and the power will be in joules per second. Another name for power is watts, but if we think about the fundamental units, it's joules per second, so it's energy per second. So every second there's a certain amount of energy being provided by the battery, and that's close enough for us to do our evaluation of our motor system. So that's the input energy, or more precisely, input power. We can ask a similar question: how much rotational energy is delivered to the load? And so that would be our, say, output energy. What do we accomplish from this power that we put in? How much power do we deliver to the load? Okay, so again, we won't be talking specifically about energy. We'll be talking about power. The rotational power can be calculated as a different product. It's the product of torque and rotational speed. And so here we've got P out is equal to tau times omega. And let's get a look at those units, okay? Tau must be in newtons times meters, or Newton meters, and omega must be in radians per second. This turns out to have a little bit of an impact later, because those are not always the units that you'll see, but those are the units you have to have for this equation to produce power in terms of joules per second. Okay, so again, we'd have joules per second, a number of amount of energy delivered every second to a load. That's just the product of torque and rotational speed, or angular velocity. Finally, we can think about the efficiency of a system by just dividing the output energy, or the output power, by the input, and the output is always going to be smaller than the input. You're going to have to put in more power than you wind up getting from your system. That is an inevitable consequence of the laws of thermodynamics. If this turned out to be 2 watts compared to 3 watts, that would be 0.6667, and we would typically express that as a percentage. We might call that 66.7%. So it's pretty straightforward. Those calculations are not hard. There is an annoyance, okay, and here is what I just want to alert you to. Okay, the units can vary quite a bit particularly in terms of torque and angular velocity, but two alternate units that come up a lot, instead of Newton meters, you might find ounce inches, which is common, but to convert ounce inches into Newton meters, you've got this number here. 1 ounce inch is equal to 7.062 times 10 to the minus 3 Newton meters. Okay, and then rotations are often expressed as revolutions per minute, or RPM. Not an unusual unit for rotation, but we need radians per second. So one time around, one revolution would be 6.28 radians, 2 pi radians, and every minute, of course, is 60 seconds. So if we want to convert from RPM to radians per second, we'd have 6.28 divided by 60, or just a little bit more than a tenth, 0.1047 radians per second. There'll be a sample problem done in the problem set, and we may use one or more of those particular conversions. Okay, so two products Voltage times current will give us the input power, and torque times angular velocity will give us our output power. Comparing those two, P out to P in, will give us an efficiency that will always be less than 100%. Okay, good luck.